I am Aida and I'm going to present the introduction, objective and conclusion for this experiment. So I'll go first with the introduction. So Torres-Lee's law, also known as Torres-Lee's theorem, is a theorem in fluid dynamics that relates the velocity of non-viscous fluid flowing under the force of the gravity. The law states that the speed of efflux, which is V, of a fluid through a sharp-edged hole at the bottom of a tank filled to a depth h is the same as the speed that a body would acquire in falling freely from a high h, where g is the acceleration due to gravity. In this experiment, we will verify the Torres-Lee's theorem using a cylindrical tank with holes. Then we will compare the measured and theoretical value of velocity. Moving to the objective of this experiment is conducted to evaluate the effect of the depth below the surface of the liquid on fluid velocity. Secondly, this experiment is conducted to verify the Torres-Lee's law by comparing the velocity using Torres-Lee theorem against theoretical velocity.
Hi, I'm Jun Yao and I will continue the presentation with the theory part. The Torres-Lee's theorem is a simplified method of estimating the velocity of fluid passing through an open orifice under static pressure. It relates the velocity of fluid leaving an orifice in a fluid filter container to the height of the fluid above the orifice. This equation is a simplification which will generally hold for simple Hall geometries where pressure loss might be essentially ignored. It is a statement in fluid dynamics that the speed v of fluid flowing out an orifice under the force of gravity in a tank is proportional to the square root of the vertical distance h between the liquid surface and the center of the orifice, and to the square root of twice the acceleration caused by the gravity. Based on the figure at the right side, the Torres-Lee's law stated that v equals to square root 2 gh, and the pressure will increase with the dip, hence the strength of the jet is increased with the dip too. In other words, the efflux velocity of the fluid from the orifice is the same as that T will have accurate by falling a height with the h under gravity. Since the velocity of the fluid coming out of the spout is the same with the velocity of the droplet of fluid that dropped from the height of the fluid in the container, hence the water stream from the hole is in horizontal direction, which can be represented by the kinematic equation as a figure at the right side. So we are going to start from the x equal to vt. The acceleration is constant, hence the xi minus x0, which is the difference of x, is equal to the vt plus with the half of a and the square root of the t. The inertial point of velocity is 0, hence the difference of the x is equal to the half of at squared. The volume V and the flow rate Q of the cylinder can be calculated based on V equal to A times with H times with W, and the Q equals to L times with the square root of 2 times with gravity times with H times with W, where the V is the velocity, the ds is the displacement of the water stream, the T is the time taken, the A is the area of the hole, the HC is the height of the cylinder tube, and the W is the y. And I am going to pass the presentation to my friend.
Assalamualaikum, I'm Afika. I present about the apparatus and methodology for this experiment. The apparatus that have been used in this experiment is clay markers, cylindrical cylinder, and measuring tape. Next, the hole at the cylinder tank were covered. Then the maximum distance was marked by using the clay and the times was recorded. And the last one, the procedure was repeated by using different volume of water and at the different height of stage, which are H2 and H3.
Hello, my name is Ahmad Zikri and I will explain to you the results for this experiment. So the data given is height of stages, which is y, and for this experiments we use three different height of stages. So for the first y, which is it is 0.36 meter, and the other data given is volume of water, which is started from 2 liter and decreasing until 1 liter, and the other data given is height of water, which is started from 0.77 meter and decreasing until 0.37 meter. So for the first data that we observed, it is the maximum horizontal distance traveled, or x. For this result, we need to have 3 readings so that we can get the average maximum horizontal distance traveled. The other data we observed is drainage time. We also take 3 readings from it so that we can get the average drainage time. So for the theoretical velocity, we use the formula V is equals to square root of 2gh, and the unit is in meter per second. So for the average measured experimental velocity, we use the formula V is equals to x times square root of g divided by 2y. Okay, so for the second height of stage, which the second y is 0.56 meter. The volume of water is the same as previous before, which is 2 liter and decreasing until 1 liter, and also for the height of water it is also the same, from 0.77 meter decreasing until 0.37. So for the maximum horizontal distance traveled, which is x, we also need to have 3 readings from it so we can have the average maximum horizontal distance traveled. And also for the drainage time, we also need 3 readings so that we can have the average drainage time. And for the theoretical velocity, we use the same formula, V is equals to square root of 2gh. And for the average measured experimental velocity, we use the formula V is equals to x times by square root of g divided by 2y, and both of the units is in meter per second. So for the third height of stage, the value given is 0.76 meter, and for the volume of water, it's the same, which is 2 liter and decreasing until 1 liter, and the height of water is the same, which is 0.77 meter until decreasing until 0.37. For the maximum horizontal distance traveled, which is x, it is the same. We need to take 3 readings so that we can get the average maximum horizontal distance traveled. And for the drainage time, we also need to take 3 readings so that we can have the average drainage time. For the theoretical velocity, we use the formula V is equals to 2gh. V is equals to square root 2gh. The unit is in meter per second, and the average measured experimental velocity, we use the formula V is equals to x times square root of g divided by 2y. The unit is also in meter per second.
Assalamualaikum and hello everyone. Today I will present the discussion part. The first question is explain your selection of dependent, independent and constant variable. For dependent variable, we choose maximum water trajectory. The discussion part. Time taken for water to drain out T. Assalamualaikum. Independent variable, today I will present volume of water V, height of orifice from flow Y. Assalamualaikum. And the constant variable is density of liquid. As you guys can see, formula on the slide for VMEA, V theoretical, we can get the constant variable, the independent variable and dependent variable from this equation. First, the constant variable. The density of liquid is constant variable in both equations, resulting a constant gravitational force. Second, the independent variable. To verify torsional relationship, we need to observe on the speed of flowing fluid from an orifice to the height of fluid above the opening. And lastly, the dependent variable. To determine the fluid velocity, we must look at how the height of the orifice from the flow y affects the maximum water trajectory distance x and the time it takes to water to flow out. The second question is clarify on how you can relate the Bernoulli equation with torsional law for this case. Show all the derivation and explain each step. We start from the Bernoulli equation. As you guys can see on the slide, the Bernoulli equation, the first point is taken at the liquid surface and the second point just outside the opening. Okay, first, since the liquid is assumed to be incompressible, the P1 is equal to P2 and both can be represented by one symbol, which is P. And then the volume. Volume 1 is assumed to be negligible since the opening is very small relative to the surface of the liquid. V1 equals 0. And then lastly, the density. The density of liquid is the same. Hence, the gravitational force G is assumed to be practically same at both points. As you guys can see on the slide, the derivation torsional law from the Bernoulli equation, P1 V1 and the P2 will be cancelled out and we get Z1 minus Z2 equal V2 power of 2 over 2G, and then Z1 minus Z2 is equal to the height of the liquid surface above the opening, which means Z1 minus Z2 equal H, and then H will be substituted into the equation. H equal V2 power of 2 over 2G. From this equation, we will get the torsional law, which is V2 equal square root of 2GH.
Okay, so for the percentage of relative error for the theoretical and measured experimental values. So for the first stage, which is the first y, 0.36 meter, we have already calculated the theoretical velocity and the average measured experimental velocity. So to find the error, we can use the formula, the theoretical velocity minus the average measured experimental velocity divided by theoretical velocity, and then to find the percentage we need to times 100%. So for the average error, there are five results. We sum all of the results and then divide it by 5, and then we can get the average error. So for the second y, which is 0.56 meter, we use the same technique, the theoretical velocity minus by average measured experimental velocity, and then divided by theoretical velocity, and to find the error we need to times the 100%, and to find the average error we need to sum all of the 5 readings and then divide it by 5. And same also for the third y, which is 0.76 meter, the theoretical velocity minus the average measured experimental velocity, and then divided by theoretical velocity. And to find the error, we need to times 100%. And for the average error, we need to sum all of the errors and then divide it by 5.
The last question for the discussion is source of error and method to minimize the error. The first error that we encounter is the cylindrical cylinder platform surface may be slightly inclined. To minimize this error, make sure the platform is flat by using a level ruler on it. And then parallax error. Parallax error due to incorrect position of eye to the scale. So make sure position of the eye is perpendicular to the reading of scale. Other than that, leakage occur around the opening of the cylinder through the space in between the finger. So use a stopper instead of the finger to close the orifice to minimize this error. And lastly, limitation in the time response in human. It might be the observer may not be able to start and stop the stopwatch at precisely the same time, or it's possibly the observer won't be able to pinpoint the exact maximum water trajectory distance. So to minimize this error, the reading should be taken several times to obtain an average result and to reduce the readings error. That's all from me. Thank you. I will pass to the next presenter.
As a conclusion, based on the calculation, the data shows an average percentage error of 9.86%, 25.33% and 44.34% on different height of orifice from the block. Therefore, the error in the value indicates that they have some errors in the experiment. So we should take some precautions to avoid the error that will affect the accuracy in the experiment. Based on the theory, the velocity of water is directly proportional to the height of the initial water level. When the initial water level decreases, the velocity of water also decreases.